Hello everyone, welcome to our animated philosophy series, where we explore timeless concepts in a modern context. Today we're diving into one of the more intriguing concepts proposed by Bertrand Russell, the idea of logical constructions. This may sound like a technical term, but don't worry, by the end of this video, you'll understand how Russell used this concept to help us better grasp both everyday objects and more abstract ideas. Let's start by breaking it down step by step. First, let's consider what we encounter in our daily lives: tables, chairs, buildings, and so on. These are all objects we easily recognize, right? But here's the interesting part. According to Russell, these objects aren't just the simple, solid things we think they are. In fact, he believed that what we call objects are, in a sense, logical constructions. So, what does he mean by that? Imagine you're sitting in a room, looking at a table. What's really happening here is that you're receiving information through your senses. Your eyes see a particular shape. Your sense of touch feels a hard surface, and so on. This data comes to you in fragmented pieces, as what Russell calls sense data. Sense data includes all the various impressions we get from an object: the color, the texture, the shape, the temperature, and we combine all of that to form a mental picture of the table. So in reality, we aren't experiencing the real table directly. We're experiencing a collection of sense data, and then our mind organizes it into the concept of a table. In Russell's view, the table is not a solid object that exists independently out there in the world. It's something constructed out of this sense data. And that's the essence of a logical construction. It's a structure we build in our minds based on the information we gather from the world. The table, in this sense, is a theoretical entity, not a concrete thing we access directly. Now, you might be wondering, why does this matter? Why is Russell going to such lengths to break down something as simple as a table into fragments of sense data? Well, it matters because this method of logical construction allows us to explain much more complicated phenomena too. It provides a framework for understanding things that aren't easily observable, things like atoms, subatomic particles, or even entire systems like economies or ecosystems. Take the example of atoms in chemistry. No one has ever seen an atom directly. We know about atoms not because we've observed them firsthand, but because scientists have constructed logical models based on experimental data and mathematical reasoning. These models allow us to predict the behavior of atoms in different conditions. In a way, the atom is a logical construction, much like Russell's table. It's not something we experience directly, but something we infer from the data we have. This concept also ties closely to the modern world of computational systems. When you play a video game or enter a virtual environment, what's happening? You're interacting with a digital simulation. The objects in the virtual world, the trees, the buildings, even the avatars, are all constructed out of data. The computer takes raw input, data points, numbers, and algorithms, and builds a virtual environment that looks and feels real to you. But just like with Russell's table, none of these virtual objects exist in the same way a physical object does. They are constructions made out of logical data sets, created to give the illusion of a coherent world. In both cases, whether it's a table in the real world or a tree in a video game, what we're experiencing is not the raw reality, but a structured construction. This is how Russell's concept of logical constructions allows us to bridge the gap between what we experience and what actually exists. To further explore this, let's talk about scientific models. Scientists often work with entities that are too small, too large, or too abstract to observe directly, like galaxies, black holes, or quantum particles. So instead of observing these things directly, they construct models based on logical relationships. These models help them make predictions about how such entities behave under various conditions. For example, in physics, we can't see or touch gravitational waves, but we can construct a theoretical model based on data, allowing us to understand their effects. Russell's insight was that logical constructions allow us to simplify complex phenomena, making them easier to study and discuss. He wasn't suggesting that tables or atoms or galaxies aren't real. Rather, he was proposing that our understanding of them relies on logical frameworks, which organize our sensory experiences and abstract data into coherent structures. What makes logical constructions so powerful is their flexibility. This framework can apply not just to physical objects, but to any domain where we rely on theoretical entities, economics, politics, social systems, and even ethical frameworks. In each case, we're dealing with models and structures that are built from observable data, but don't necessarily represent tangible, material objects. So to recap, Russell's idea of logical constructions helps us understand the world not just as a collection of objects we directly experience, but as a network of structures built from sense data, inferences, and logical relationships. Whether we're talking about a table, an atom, or a virtual world, what we see and interact with is a construction that makes sense of underlying data. This concept of logical constructions resonates deeply in today's world, particularly in fields like science, technology, and philosophy. It shows us how we can use logic and data to explain things we cannot directly observe, allowing us to construct meaningful representations of complex phenomena. And just like a computer game simulates a world from lines of code, we too simulate our understanding of reality through the logical constructions we create in our minds. That's the brilliance of Russell's idea. It provides a tool for navigating both the physical and abstract, making the complex a little more manageable and opening the door to deeper understanding across many fields. Thank you for learning with us. Don't forget to like, share, subscribe, and hit the notification bell for more insights into similar echoes.